Hello everyone, I am Dr. J. Johnsy, Assistant Professor, Department of Mathematics, Fatima College. In this lecture, we will study eigenvalues, eigenvectors, diagonalization, and principle of mathematical induction. Welcome to Module 1. In this module, we will learn characteristic equation of a matrix, definitions of eigenvalues and eigenvectors, Cayley-Hamilton theorem, and see how eigenvalues and eigenvectors are calculated from simple examples. Characteristic equation. The determinant of A minus lambda times the identity matrix I equal to 0 is called the characteristic equation of a square matrix A. The values of lambda that satisfy this equation are called the eigenvalues of the matrix. Here, I is the identity matrix, lambda is a scalar. The roots of this equation are called eigenvalues. Next definition, eigenvalues. A scalar lambda is called an eigenvalue of a square matrix A if there exists a non-zero vector x such that Ax equals lambda x. This vector x is called the eigenvector corresponding to the eigenvalue lambda. Here is an example. Let the given matrix be A equals 2, 1, 1, 2. Find the eigenvalues. We solve the characteristic equation determinant of A minus lambda I equal to 0. We first write the identity matrix and multiply it by lambda and then compute the matrix A minus lambda I. After forming the determinant and simplifying, we obtain the characteristic equation lambda square minus 4 lambda plus 3 equal to 0. Solving this equation gives the eigenvalues 3 and 1. Next definition, eigenvectors. A non-zero vector x satisfying the equation Ax equals lambda x is called the eigenvector corresponding to the eigenvalue lambda. Here is an example. For lambda is equal to 3, then A minus 3 times I into x equal to 0. Substituting lambda equal to 3 in the equation A minus 3I into x and solving the system of equations gives the relation x is equal to y. Then let x is equal to 1, then y is equal to 1. Hence, the eigenvector corresponding to lambda is equal to 3 is the column vector x that is equal to 1 and 1. Next, find the eigenvalues and eigenvectors of A equals 4, 1, 2, 3. The computation procedure for finding the characteristic equation is determinant of A minus lambda times I equal to 0. Then lambda square minus 7 lambda plus 10 equal to 0 is the characteristic equation. Then after factorization, we'll get lambda is equal to 5 and lambda is equal to 2. To find the eigenvector for lambda is equal to 5, so substitute lambda is equal to 5 in the relation a minus lambda I into x equal to 0, then we'll get the relation x is equal to y. Taking x equal to 1 gives y equal to 1. So therefore the eigenvector for lambda is equal to 5 is the column vector 1 and 1. Next, to compute the eigenvector for the eigenvalue lambda is equal to 2, then a minus 2i into x equal to 0. This gives the relation after the computation y equals minus 2x. That is, let x equal to 1, then y equals minus 2. So therefore, the eigenvector corresponding to the eigenvalue 2 is x is equal to the column vector 1 and minus 2. The next concept is Cayley-Hamilton theorem. The Cayley-Hamilton theorem states that every square matrix satisfies its own characteristic equation. This theorem is very useful for simplifying powers of matrices. Consider the matrix 1, 2, 3, 4 to verify Cayley-Hamilton theorem. The characteristic equation of the given matrix is lambda square minus 5 lambda minus 2 equal to 0. For using determinant of a minus lambda equal to 0, then we have to prove that a square minus 5a minus 2i equal to 0. So this is the computational steps. The first step, to compute a square and 5a and 2i, then substitute, we'll get the 0 matrix. Hence, the Cayley-Hamilton theorem proved. Conclusion. In this module, we learned the characteristic equation, the definitions of eigenvalues and eigenvectors, and solved examples to compute them. We also introduced the Cayley-Hamilton theorem and the verification of this theorem. Thank you.